Thank you very much for your introduction. My name is Kamimura from NF Corporation. Today I'm going to talk about the low noise technologies for quantum computing. First, let me introduce the company. 1965, the company started. This is the startup company from university. This is a leading company in the measurement control machinery. 1961, the first oscillator was created by our company for the first time in Japan. So we are very good at the low noise signal detection technology. And one of the example is the Japan's first FLL system for brain magnetic field measurement using SQUID. So low noise amplifiers and low noise detectors were developed at that time. So now in the quantum computing, it is very important to enhance the readout fidelity. And this is example of the quantum computer layout. And around the computer, the flow noise, amplifiers, and then power, and few other peripheral devices. If you look at the middle, this is one example of the readout characteristics. Orange shows 0, and the blue shows the location. And the 0 and also the 1 overlapping, it is not ideal. If you look at the right-hand side, against the readout fidelity, noise, and also the amplifier gain, and power supply voltage, these interactions. When the noise is high, the signal intensity and also phase are varied, and therefore that there are problems. And due to the power supply voltage and also amplifier gain changes, 0 and 1, the distribution shapes changes, and also distribution itself may expand. Again, it is not ideal. Low noise and low impact from the environment, then the 0 and the 1, these overlaps is solved, and readout fidelity becomes higher. So low noise and high stable environments are very critical. So quantum computing's peripheral device should be low noise and also high stable devices. This is the products which we produce for quantum computing. Let's start from low noise amplifier. Annealing quantum computing DC amplifier and also the AC amplifier for gate. Due to time constraints, gate type quantum computing and down conversion and amplifier used for that is going to be the topic of my talk. So in the gate style computer, we need to have a high frequency amplifier, which is around 50 ohm. Left-hand side upper corner, find the typical amplifier circuit configuration, and 50 ohm resistance goes to amplifier. Right-hand side, the x-axis is absolute temperature, and the y-axis is voltage noise density, and 50 ohm heat noise is shown here. In the 300 Kelvin, the room temperature, the 0.9 noise means that it is very difficult to reduce the noise. But if you look at our company's circuit configuration, then we use the active impedance method. So input is set at 50 ohm, and at the same time, heat noise can be minimized. And the amplifier has the unique low noise design, and due to that we can have less noise. And if you look at the right hand side, using in the room temperature and 50 ohms heat still produce the low noise almost as same as freeze cooled by the liquid hydrogen. So let me introduce how we do this. The left-hand side is the noise performance of the amplifier, and x-axis is frequency, y-axis noise figure. 0.9 decibel, very small or very low noise characteristics. On the right-hand side, this is a reverse transient gain, is the y-axis, and also the x-axis is frequency. The minus 80 decibel, lower than the minus 80 decibel, and the design is in such a way that it does not receive any impact from the amplifier. Now, moving on to the stability of the gain. Left-hand side is the heat dependence of the gain. So in the actual measurement, 0.00042 decibel, so it doesn't get almost no impact from the temperature. Right-hand side, these are the voltage dependence on the gain. So power supply voltage and also gain variation. And actual measurement is again 0.003 decibel. Doesn't get almost no impact from the power supply voltage. This is the appearance of the device and also the specifications. So this is easy to input or integrate into the multiple devices, and you can line up 8 different devices in the length of the ballpoint pen. And you can find the specification on the right hand side. Low noise and at the same time stable gain is 40 decibel, so that the readout fidelity becomes higher. 50 ohm amplifier is used here, but other than that, we also have the high impedance FET amplifier. So hopefully that we can get these specifications. And now I would like to talk about the low noise direct power source and also the voltage source. As you see that these are the noise impact of the power source to the amplifier. Regularly speaking, the high frequency RF amplifier is susceptible to the power source noise. The right hand side, you can find the wave shape of the amplifier's output noise. The upper side is a regular linear power, and the lower side is our company's power source. As you see, the difference in the power source give the great difference in the noise level. The left-hand side is the power source output noise performance is shown, and the x-axis is the frequency, and the y-axis is the voltage noise density, and the blue line is a regular noise, and the red line is our company's noise level.
から広域まで低ノイズになっており、アンプに影響を与えないような構成になっております。
So in this way, because the amp is impacted, and because of this, this has the impact on the readout fidelity. So the lower noise of the source is a very important element. What you see here is the diagram of the system of the quantum computer. The quantum bit is located within the refrigerator, but because the signals from the bit is very small, so we need to have the JPA hemp amp and also RF amps to enhance or amplify the signals. To do this, we need also the supplies and also direct supplies and also voltage source. And first, I would like to talk about the RF amp direct current power supply, which satisfy the requirements for low noise, high stability, and also the drive current of 100 mega ampere per CH. So this is the important points. And you see here is the block diagram of the DC power supply. In addition to low noise design of the analog section, low noise AC-DC converters, isolation circuit designs to block noise in the digital section, and disturbance countermeasures such as double shieldings are used. For thorough low noise design is implemented. And as a result, we achieved the low output noise performance of less than 50 microvolt RMS. Next, we worked on the temperature stability of the DC power supply. You see the temperature on horizontal axis, and also the output is shown on the vertical axis. We have developed unique temperature compensation technology and highly stable internal bias circuit technology. And the measurement results of the temperature dependence of the output voltage is shown here on the horizontal axis, and the ambient temperature is indicated. The vertical axis indicates the amount of output voltage variation. And the development technology realized an actual measurement value of 1.2 ppm per second per degrees. This shows the appearance and specification of the DC power supply. The lower left figure shows the product. It has 16 output channels in the size of a 19-inch rack with a height of 2U for multiple qubits. Has multi-core connectors for the output connectors, and the output of 16 bit channels are consolidated into 2 connectors. This reduces the number of cables required even when the number of qubits increase. Next is the DC voltage current sources for qubits, JPA, and HEMT amplifiers in dilution refrigerators. And this shows the how bias source is used. On the left side, you see the diagram of the JPA. And inside JPA, squid is used, and this controls the boards with qubits on them with the very weak magnetic field, and the bias source is used to manipulate this. As a result, because of this, you need to have a very high stability. Also, there is residual magnetic field inside, so you need to have the bipolar. On the right side, HEMT amp is shown on the right side. HEMT amp uses the needs to control VD and VG strictly accurately to set the proper optimal driving point, and therefore we have the requirement for a bias source that realizes high setting accuracy, and we did develop that. So now I would like to talk about that device source, that bias source. But before that, now care must be taken with the ground potential of the bias source in directly controlling a board with multiple qubits. This shows the case the ground source are shared common, or the other ones are separated. If the bias source is not isolated between channels, a ground loop may be formed, allowing for the disturbance noise. Also, depending on the qubit configuration, the return current may need to be precisely controlled for each channel output. If the ground potential of each channel output is common, multiple output return paths are formed, making it difficult to control the return current. As a solution, a channel-to-channel isolated voltage current source is required. We have developed a voltage current source with channel-to-channel isolation and low noise performance to meet these requirements. This is the block diagram of the developed DC voltage source. This DC voltage source achieves low noise characteristics while minimizing increase in product size. We have developed a new compact low noise isolated DC-DC converter for this purpose. In addition, each power supply system is designed to be double-sheeted to prevent external noise. As a result, even with channel-to-channel isolation, the product size remains almost the same. And you see the specification, the performance here on the left side. You see the noise level of the bias source. Horizontal line shows is the frequency, and vertical you see the noise density of the output voltage. And the noise level of the power source is 1 micro VRMS, and the current source noise is 2 NARMS. So the world top level low noise performance. And on the right side, you see the temperature dependence of the voltage and current source. And the voltage source has the temperature stability of 0.8 ppm, and the current source temperature stability is 1.5 ppm. Here are the appearance and specifications of isolated low noise DC voltage current source. As I said earlier, they deliver extremely low noise performance and also high stability. So they are perfect choice for quantum bit JPA hem-to-amp control. Also, the output are channel-to-channel isolation provided, so they are appropriate for different systems or elements. So NF develops and supplies low noise and highly stable devices for quantum computers based on the microsignal measurement technology cultivated over the years. As a leading measurement and control company, we hope to contribute to the quantum computer field by creating new value through creativity and technology. Thank you very much.